So just a quick reminder, there's a whiteboard in the hall. Please propose your lightning talks and vote for them. And our next talk is Security Development Lifecycle in Open Source.
Hello. Welcome to my presentation. I'm Rusnačko. I work as a product security engineer at Red Hat. This talk will be about Security Development Lifecycle in open source. So the Security Development Lifecycle is a term coined by Howard and Lipner from Microsoft in their rather older book. So the Security Development Lifecycle is basically a usual development lifecycle with the security added to each of the phases of the lifecycle. Now there are several myths about the security. I'd like to start with a few. First one is the coined by Linus Torvalds, given enough eyeballs, all bugs are shallow. So this is an intuitive thing, which we all rather tend to believe in open source. However, at least for security, this is completely not true. So in contrast with finding bugs, finding security features requires good security knowledge and experience on the part of the reviewer, and is difficult to find with usual testing, because the product works even if it's insecure. Now the myth number 2 is not a quote, although I put it in a quote. It's an intuitive thing that we think that the discovery of vulnerabilities closely follows the model of finding bugs. So for bugs, it holds that the older the software, it tends to be more stable because it's more tested by the users. And the better code reuse leads to less bugs, because reusing components that are tried and tested usually doesn't introduce that many bugs. However, for vulnerabilities, complete opposite holds. There is a very nice paper, which I recommend to you all, by Blaze et al., Familiarity Breeds Contempt, where they actually found a few rather intriguing things. So first, they figured out that the older the software, the more vulnerabilities tend to pop out. And even more interestingly, code reuse actually leads to more vulnerabilities in a software. So how can that be? So they argue that the most important thing in finding vulnerabilities is the familiarity of the attacker with the code base, which tends to be better with time. So they gathered a data set of 30,000 vulnerabilities, and their data showed that the first vulnerability found in the software usually comes in later, after the release, usually several releases after the first one where the vulnerability was introduced. So this is a rather intriguing idea. So our trouble in open source is that we do the development, we test our product, we release it, people start using it, and only after our software is used, then the security researchers start looking for vulnerabilities, and they start to pop out. I call it the denial of development attack, by finding so many vulnerabilities that the project basically has to enter an infinite loop of fixing them. No further comment if you're familiar with Google Project Zero. So a little bit of a small puzzle for you. You can guess the name of a project. Yeah. I figured that after the first talk, this will be pretty obvious. Yes. This is OpenSSL. So good guess. So you can see, obviously, that in 2014, after Heartbleed, it became cool to find the vulnerabilities in OpenSSL, and they had around 25 just last year. So the original SDL by Microsoft, this is the outline, basically. It starts with the education. So before we even start writing any program, we need to educate our developers in security, and we need to define best practices and create the risk analysis, create the secure coding policies, and so on. So the structure is based on a timeline on the development cycle, and they describe the security in each of the phases. There is also another model by OWASP, which is Secure Software Assurance Maturity Model. This one is maybe a little bit better for open source. It defines 4 business functions and 3 security practices. It's not important. And for each of them, defines 3 maturity models. So for each of them, you should strive to get to the 3rd one, which is comprehensive mastery of the practice. And these are the practices. Some of them are easy to acquire in open source. For example, code review. That's what we usually do, but for other policy and compliance, that's usually harder to get in open source. So, open source development model. We all know how it starts. It starts with a cool new project, whether it be free time project or school project. We rush to get the first working version out. We add features based on customer or user demand. Monetize the product by making a cooler UI theme and make it enterprise. Now, question is, how do we fit the security into such life cycle? That's a not trivial question. So I chose a few topics from both models, both from Microsoft one and OWASP, which I'm going to present. First one is education. That's absolutely necessary. If the developers are not educated in security, obviously will create more vulnerabilities. Thankfully, there are a few good resources available. I'm referencing mostly those that are created in open source. So first two are on Fedora docs. They're also mentioned by Huzaifa in his talk. OWASP has a good documents. They are very readable, so I can recommend them. And that's it for this slide. Actually, there's not much for here. I wanted to make it proportional. The time I spend on this slide to the time the developers usually spend educating themselves in security. Unfortunately, it's not much. So, design best practices. There is a very nice document released by a Center for Secure Design. It's actually a few folks from industry coming together and compiling the list. The list is very readable. It's a not long document, so I very recommend reading it. The design flows are rather intuitive. For example, the third one, authorize after you authenticate. That's very common mistake. I would argue that the sixth, use crypto correctly, is these days basically impossible to achieve, given the state of the crypto libraries that we have, but one can try. So security docs, tools, and best practices. These are great topics for blog posts if you're open source project. I recommend writing a blog about the security of your project. It allows customers or your users to configure it securely, which actually increases security a lot, because security misconfiguration is a very common problem, and it serves as a good marketing for your project. So, now this is a big topic: security testing. This we should do more of the security testing. Now, when I talk about security testing, is not the same as testing security features. So I like the example of RBAC in a web application, if you implement a role-based access control, you usually want to the roles to be authorized per role, and if the RBAC fails and users from one role can acquire more permissions than they should have, that's a bug in a feature, right? That leads to vulnerability. However, when we are security testing, we also want to we try to deliberately find the vulnerabilities in a feature. So we shouldn't stop there. We should also try to find, for example, cross-site scripting in a role field or form in a web application, which is not usually done during testing. So when you're trying a security testing, your QA team needs to have a good strategy here, because just randomly writing some tests does not any good. There is a good reference in the OWASP testing guide, which is unfortunately very comprehensive. It's like 60 or 70 pages. So I've seen and worked with QE teams in Red Hat, and they usually go through the OWASP top 10 and just try to make sure that for each of the most common weaknesses in the top 10, they have a comprehensive security tests written for their application. Fuzzing is very popular these days in security community because it's a very cheap way to find new vulnerabilities. There are a few types. First is down testing, which is basically feeding a random input to your application. There's not much more to it. Second is a little bit smarter fuzzing with the American Fuzzy Loop written by Michael Zalewski. It's a little bit more smarter than the dumb fuzzing in the sense that it instruments the code of your application and tries to generate inputs that will test more code paths. So it usually has much better code coverage. And smart fuzzing means you literally write your own intelligent fuzzer based on a protocol input specification to your application. Now, when you're a security team and you try to choose between those, there's a trade-off. The amount of time you spend setting up the fuzzing and the amount of time you spend actually fuzzing it. So in the dumb fuzzing, it's 5 minutes until you have it set up. In smart fuzzing, it can take weeks. So usually the best trade-off is a smarter fuzzing. It's as easy to set up as a dumb fuzzer, but it has better code coverage. Now another tool in the security testing is static code analysis, which we also have at Red Hat. The experience shows that this creates a lot of false positives, and it's very hard to go through them. So it's very recommended to set it up such that every report contains only the differences from the previous one. So the developers or the QE team only has to go through the warnings that were introduced since the last report. There's an example for Brakeman, which supports the diff reports out of the box. If you're testing web application, it's a good idea to set up a scanner. That's also a cheap way to find the vulnerabilities. However, they're pretty dumb. They have their inherent deficiencies. They basically don't know anything about the application, so it's a black book testing. And since they're automated, they're not very creative. So they can try usual attack vectors like cross-site scripting, but you never know. That's a good smoke test, though. So the example setup that I would propose for an open source project is include into your continuous integration security tests that your QE team writes and a static code analysis. That's very important because you don't want to go through hundreds of warnings before the release. And before the release, set up fuzzers or run web application scanners. That's a good smoke test before. Now this is, I guess the most tricky part of the development lifecycle, how to do code audits efficiently. The difficult thing about it is it heavily depends on the skill and experience of the auditor, which is these days, scarce resource. So there are two ways to get around this. You can either prepare a good plan before the audit and follow it. You have to basically avoid diving too deep into certain code paths, and also you need to verify structurally that not only these few chosen vulnerabilities are not present, but make a more comprehensive review. The other part, more fun, is organizing a hackathon. Again, from experience, they're very efficient in exchanging security knowledge between the members or participants of a hackathon. That's a great side effect. They also tend to find a lot of vulnerabilities quickly. However, it's very hard to make any assurance about the security of the software afterwards, because it's the participants don't follow the structured effort usually. Now the tricky part is a security response for open source projects. Before you release your project, I suggest you need a few things. At the very least, you need a security contact on your project webpage, where users can report vulnerabilities. This was actually one of the questions on Zaifa's talk, so that's a quite common problem. And you need a security response team. Doesn't matter whether it's formal or informal. It can be a one developer, which is dedicated to fixing the security flaws and handling the response. And you also need a clear vulnerability management plan. There is a good example in Open Daylight vulnerability management plan written by our former colleague. It's very readable, and I suggest you take it as a good starting point. The good plan should have several parts. It should clearly describe the process around retrieving the reports and initial triage of the flaws, creating a patch in private, and requesting a CV for a vulnerability. And the most tricky part is disclosure coordination. Yep. So, as an example, to give you a feeling how disclosure coordination can be tricky, the main goal of the disclosure is your project is usually consumed by several vendors, whether it be Red Hat, Novell, or Google, or other vendors. And if a vulnerability is found in these projects, it's usually a good idea to develop a patch, disseminate it to these vendors so that they can prepare security advisories and then agree on a common release date, so that when the common release date is reached, all the vendors can release their security advisories together, so that there is no risk to the users. So this is a timeline for Heartbleed. It was found on 21st of March by a Google engineer. 10 days later, they notified the OpenSSL, but it's also independently found by a fuzzer at Codenomicon. 3 days later, it's important to register a domain for it. On the 7th of April, Red Hat and distros were notified, and that's when it got, panic, into panic mode. OpenSSL released advisory prematurely, a few hours, so only a few hours were given to the vendors to prepare security fixes. At 6 o'clock, Cloudflare published their blog post, again for good PR. And hour later, Heartbleed was a good spark in a panic that followed the Heartbleed. And 2 days later, we hit a agreed upon common release date, right? So that's how it goes. Again, shell shock. That's a good one. It was found by Stefani Chozelas. He notified major vendors. Fixes were created, distros were notified, and coordinated disclosure date was hit. The patches were available. So, win. Everything was great. A few hours later, Google engineer, let me stress this, tweets about incomplete fix in the that was disseminated by the vendors, and the panic followed. So the disclosure is usually a tricky part. The problem is that, unfortunately, a recent trend is to use a vulnerabilities such as these for marketing purposes. Is a little known that Stefani, the original reporter of a shell shock, proposed a code named Bashdoor. However, by that time, security marketing was already established discipline, and that was not cool enough. So media went with the shell shock. So we have security development lifecycle in place. What else? What next? What's next? We need to close the loop. We actually need to evaluate the vulnerabilities which we receive for our project, and use a feedback to improve our development. Good framework for this is a common weakness enumeration by meter. That's a standard, let's say, vocabulary for classifying different kinds of vulnerabilities into so-called weaknesses. And this helps when talking about the types of the weaknesses. So what we do at Red Hat is we classify every vulnerability, assign it the CWE, and we see which types of vulnerabilities are most common. So this is a statistic for the 2014 of the flaws in open source. These are all of the vulnerabilities that appeared in our Mozilla. So you can guess which one was the top one. It's buffer overflow or buffer problems, whether it be, overrun or read or write or stack or heap. The second one is more surprising. It's a cross-site scripting. And then general input validation, insecure temporary file. Denial of service is pretty high too. So when you have these stats, these can help you with putting mitigations in place. For example, if you see that insecure temporary file is so high, it may be usually a good idea to create something like a poly-instantiated temp and give it a priority to actually kill a whole class of vulnerabilities that can appear. That will save you a lot of effort. So that's it. These are references for my presentation. And are there any questions? Yep. Yep. Right. So it's not a. Yeah. Sorry. How many of these can be mitigated by setting up your application within containers, right? I would argue that containers don't contain. They're usually not a security panacea. Also, it depends a lot on your on the assets that you want to protect. For example, if you have a web application that serves confidential data and you have RBAC, it does not help that your web server is contained from the rest of the server, because the asset that you care about is the content that your web server serves. So if the attacker compromises the server, he gets the data, right? He doesn't care about the virtual machine or the container that you can, tear down and set up as many times as you want. So it helps a little bit. Also, another thing that you need to be aware of is that setting up another component in your stack, which is a containers, right, usually increases attack surface. And you know that from the number of CVs that, for example, Docker received last year, right? Other questions? No. All of them have problems. So different languages usually tend to have different vulnerabilities. C, that's usually buffer overflows, right? But even if you kill the vulnerabilities such as this one by having a good memory management in dynamic languages, such as Ruby, you usually end up having a different kind of vulnerabilities. For example, Ruby has a lot of deserialization flaws because of Rails or cross-site scripting, right? Because it's usually used for web development, right? So in the end, you only end up with different kind of flaws, but you never, solve the problem. Okay, thank you.